Hello, my name is Jorge. I come from Spain, and today I'll be speaking about my project about how I characterize the variable star EPIC 246257206 discovered with data from the Kepler Space Telescope. So the main research objectives were to find the variable star in the Kepler Space Telescope database, understand why the brightness of the star varied over time, and to do that, you need to calculate the period and the amplitude, and finally, to publish these results in the International Variable Star Index. Before that, I just want to mention some brief concepts that are needed to understand the experimental process and the conclusions of the research project. The first concept that I have prepared is the concept of a light curve, where it's a plot that in the y-axis, we've got the brightness of the star in units of magnitude. It is an inverse scale. And in the x-axis, we've got the brightness of the star in units of Julian date. If the star is variable, we can see that the observations do not line up in a horizontal line parallel to the x-axis, but they will oscillate through time. And most of these variable stars are periodic, meaning that this oscillation, this pattern that eventually will tell us why that star varies, will repeat over time. And if we do not have enough observations to see this pattern nicely, we can superimpose all cycles, all observations, and obtain a new plot called the phase plot. This plot will tell us exactly at which moment in the cycle was that observation taken. And for that, we need to define a new magnitude called phase, which is the integer, which mathematically is defined as the integer, as the decimal part, sorry, this was a mistake, of this quotient, which is the time of the observation was taken minus the initial time of the cycle divided by the total period of the cycle. According to the general catalog of variable stars, we can define 5 different groups of variable stars, and more in particular, eclipsing variable stars consist of binary systems where 2 stars orbit periodically around their common center of mass. When the big star eclipses the small star, we're going to see a primary eclipse, so a primary minimum in the light curve. And when the second star eclipses the big star, we're going to see a secondary eclipse in the light curve. Using this idea of the light curve be consisting of 2 eclipses, we can define 3 different types of eclipsing variables. The first type is the EA type, which consists of very well-defined eclipses, and outside those eclipses, there is no variability. In the EB types of eclipsing variables, the eclipses are still well-defined, but there is some sort of variability outside those eclipses. And finally, we've got the third type, which is in constant change of brightness, which is the EW type. Quickly, I just want to mention the concept of parallax that is mainly used in astronomy to calculate distances to nearby stars in our galaxy. So when we observe a star in January, we see that it has a position relative to some background stars. And when we observe it 6 months later in the other side of the sun, it has a different position regarding regarding the background stars. Comparing these images, we can obtain this angle here that using some simple trigonometry, we can define the distance of the Earth to the star as 1 astronomical unit divided by the tangent of the angle. As I said, I used the Kepler Space Telescope to find a variable star. And I used this because it used photometric data, that means brightness over time, and its main focus was to find exoplanets, and to do that, it used the transit method. It studied the photometry of the star, and it looked for depth in the brightness of the star. That means that a planet has gone in front, similarly as in the eclipsing variables, producing a depth in brightness and an eclipse. Like its photometric observations, brightness over time, and we've got a cadence of every half an hour, we've got a data point. It was a perfect way to get incredible amounts of data to find a variable star. More in detail, I decided to mine the database in the second part of the mission, in the K2 mission. And more in detail, I used the field of view of campaign 12, which was centered in the constellation of Aquarius, which is favorable to see in the winter months when this observation was taken. In this campaign, I used a process called data mining, and I only looked at those stars that were bright enough to be observed from Earth and with the available equipment. The star that I was looking for had not to be cataloged, and it had to be a variable star. To do that, I checked the Vizier database constantly, and also the period of the star had not to be longer than one night to then observe it from Earth, to not have to see it in more than one night to obtain enough data to characterize it in one night. Then, in this campaign, I found the star epic 246-257-206, which from data from the Gaia spacecraft, I obtained its parallax angle and found that it was about 700 light years away from Earth. Later, I had to check that the Kepler photometry was valid because I wasn't responsible of obtaining this data. So then I used the Panzer's telescope in Hawaii, which provided me this image, which is high definition, which is very high definition, which covers a greater field of view of the Kepler image, which is this one here. These pixels are very big in size, relatively big, and there might be a faint star that in this constant doesn't appear in the mask, but it does appear in our data. Therefore, using this data from Kepler, you can say from Pan-STARRS, we can say that there is no fainter star in the field, and therefore the data from Kepler is valid. Further on, I observed it from the ICTA observatory in northern Spain, where I obtained images like this one, which using a process called aperture photometry, I compared the flux arriving to the variable star in question with two other reference or calibration stars. Knowing the magnitudes of the brightness of these two stars, I can obtain the magnitude, which is the brightness of the variable star. Having all this data, and so the K2 data, the data from the ICTA observatory, and the data that Faustino Garcia, an astronomer from the Omega Astronomical Society, provided, I could obtain the light curve. And using a mathematical tool called the Lumskargli periodigram, I looked for periodic signals in our data, we can see I obtained this graph, which for every possible period, it obtained how powerful is that signal. We can see that there are two peaks. The first peak corresponds to every time, which is more frequent than the second one, corresponds to every time there is one eclipse in the light curve. And the second one corresponds to every time there are two eclipses in the light curve, which by definition is the period of a variable star. So using this, because this peak is double the size of this peak, in period. So having this period calculated, I was able to obtain the phase plot, which allowed me to obtain the pattern that we're looking for, that will eventually tell us that it consists of an EA type, because comparing it to the light curve at EA type, we can see that this star is an EA type. So what's causing the variability of star is that it consists of a binary system that they orbit periodically around their center of mass, producing eclipses as seen from Earth. But most interestingly is the amplitude of the star of only 0.05 magnitudes. And I suggest that this is because they're grazing eclipses. So in the plane that we are observing it from Earth, the stars do not eclipse totally, but partially, meaning that not all their surface is being blocked by the other star, and the shadow that's projected to Earth, the eclipse, is much smaller. Anyway, this was enough to publish the data in the variable star index, which was reviewed by the moderators of the catalog, and they agreed with my conclusions. And also, I just want to say how the importance of this project and its contribution to the search of an Earth 2.0, so to other planets similar to Earth. When we find a transit depth at a transit, we have these three transits here, for example, which are more U-shaped. But grazing eclipses in eclipsing binaries present also very low amplitudes in brightness, so very small depths, but they generally are more V-shaped. But this is a very small difference, and computers do not normally find this easily. So it is essential that we find the whole population of these stars in our galaxy, so we can take them off of the possible transit exoplanet candidate lists. And briefly, just want to say that this project allowed me to characterize and find other variable stars as we have here. And thank you very much for your attention, to all institutions that helped in this project, and for this committee to allow me to present my project today.
Thank you for your presentation. We have a time for one brief question, and we will move on.
Jorge, thank you for your presentation. So you actually discovered a new star for a catalog, yes?
Yes, I'm being recognized as the discoverer, yes.
That's very cool. Congratulations.
Yes.
With that. And did you have access to observatory yet?
Yes, I had access to the observatory of this institute, of the ICTA Institute, which is part of the University of Oviedo in northern Spain.